Yeah? Okay. Good. Then let's start. And today I will finish by 3:30 because I have to go to another meeting. And I'm not sure I will cover everything that I plan to cover. But anyway, then we'll maybe extend the lectures for one more week. Okay, so today we talk about discrete Gaussian distributions, which turn out to be the right way to define distributions on lattices so that we get nice results with good parameters and everything, and nice, elegant proofs. This originally simplified already the original results by Aitai that showed this worst case to average case between lattice problems. And it turned out that when Oded Regev and Daniele Micciancio did that in the early 2000s, things became, once you took that mathematical burden or hurdle of talking about Gaussian distributions, things became much easier, much better, and much more elegant in a way, and that cleared the way for many results. But actually, this was not the first time that people looked at these Gaussian distributions on lattices. The first really breakthrough result were by Banaszczyk in the early 1990s, where he proved optimal versions of the so-called transference theorems. Anyway, so discrete Gaussian distributions. So it's probably best to start with the standard Gaussian or normal distribution on R. And so now we are talking about continuous distributions. So we don't have a probability distribution, we have a density function. And well, the meaning will become clear in a few minutes. And the density function for the Gaussian or normal distribution with mean C in R and standard deviation S in R plus is defined to be this animal here, NCS of x. It's 1 over square root 2 pi s, and then the exponential of minus of x minus c squared divided by 2s squared. And that's true for all elements x and R. That's the density function of the Gaussian distributions. If you want pictures, you have seen these things. So they look like this ball-shaped curves where the mean is always here. You look at the peak here and here, where is the peak. And then the deviation we'll talk about in a second. Okay. You see that this expression, this function here, has its maximum clearly when this term here becomes 0. Okay. Because then this becomes 1. Okay. It cannot become larger than 1 because this is positive. This is why we have S in R plus. So this is always positive. So the argument for the exponential is negative, so or not positive, non-positive. So it can be at most this whole expression can be at most 1 for S is equal to C that it is 1, and then we have that this value is 1 over 2 pi square root 2 pi S. So the peak here always says where the density function is maximal. Also, obviously, the whole thing is symmetric around C because of the square. Okay, so we always have these nice little curves. Okay. In lattice-based crypto, I should say that in this case, if you now compute the expectation of this distribution with this density function, then you will get exactly that this is C. So what is the distribution? So the expectation of the Gaussian distribution, I'll just do this, n c comma s, is the integral over all of R, and then you take just x times n s comma c, c s of x dx. That's the expectation. It's like the expectation in the discrete case, except that we replace a sum by an integral. And similarly, you can define the variance and standard deviation, and turns out that S is really the standard deviation. Okay? And also the integral, this integral over all of this is really 1. So we really have that. This is a density function in the sense that over R, integral over R, n cs of x dx is 1. Right? So, and we can actually say, so this is C, and if you want to have S, you look at the expectation of n s comma c comma s minus c squared, and then you take the square root of this. Okay. This is like the, without, inside the square root, this would be the variance, and the standard deviation is the square root of the variance. And you remember that we always take the square. We want things to be symmetric. You take the square because, well, you really would like to take the absolute value, but the absolute value is, in some cases, an annoying function because at 0, it's not differentiable. It's continuous, but not differentiable. Taking the square makes life much easier because you can use analytic methods in that case. Okay, so that's why. So that's where we get these two parameters, C and S. Okay. For lattice-based crypto, it has become customary to use a slightly different function. Namely, we include a pi here, drop the 2 in the denominator, and call this rho s comma c. And we also change the order of C and S. Okay. Then it turns out that the integral over this function is S. So this is not the density function of a distribution. You have to normalize it by 1 over S because the integral over this thing is S. Okay. Which you can easily see by looking at the density function for the standard normal distribution, and then you take the substitution, use a substitution rule from integration theory, and you see that this is S. Okay. This has become somehow, it doesn't really matter, but this has become the usual way to define these things. It has some nicer properties, and we don't have to do it always work with this 1 over 2 square root of 2 pi. Okay. As we later see, we often take a ratio of such things, and then this 1 over s goes away anyway. Okay, so that doesn't really matter. But in some cases, we actually use this ds comma c. Okay. But other than that, it's all the same. When we have kind of random variables. A random variable w is distributed according to this dsc if for all a, comma b and r, a at least not larger than b, we have that the probability that the random variable falls into this interval ab is exactly the interval ab dsc of x dx. So the probability, that's why it's called the density, it's a density function, right? The probability that it lies in that interval, a random variable, if it's distributed according to this dsc, then this is given by this integral. Yeah, this is the same as we have here. Okay. Okay. And An interesting thing that explains many of the properties of the Gaussian distribution is this concentration bound, which there are many versions of it. This is probably the easiest statement of it. Assume that X is distributed according to this distribution DSC. Okay? Then the probability that X is in an interval around C of width RS or 2RS actually, right? Because I take the absolute value. Okay? Where S is this standard deviation. That's upper bounded by 2 times e to the minus r squared divided by 2. So if you look at this interval, so here's our C. Usually you can take C to be 0. And then you take these intervals. Okay, so this is, say, S. And then you have this 2 times S. So this is 2S and so on. And then you can make this even larger. And then you have this R times S. The probability of getting a value that's outside this interval drops exponentially fast with R squared even. Okay. Okay, and this is, by the way, there's also a converse, sort of converse is also true. If you want to end up in a certain interval with constant probability, you need that interval to have width at least a constant times C. Okay? Otherwise, you don't have constant independent of S. Right? You can actually see that with a normal distribution. Actually, this is probably true for both things. If you look at this thing here, the original definition at axis C, we have 1 over 2 square root 2 pi S. That's not a constant probability because we don't consider S to be a constant. We want something that's independent of S. So you have to have a certain width around C to get a constant probability. And that width is at least roughly square root S, or a constant times square root S. Okay? If you don't go around your expectation by some constant fraction of the deviation, you will not get a value that's with a constant probability. That's not just true for the normal distribution, that's true for almost any distribution. You have to get around this thing, around standard deviation things. The interesting thing is maybe that we only take, we have to, you can think of it, well, at 0 you have 1 over 2 pi S, so I want this to be constant, so I should take this like a width of length S. Yeah? So you can easily see that, right? If you look at this thing here, the integral, and then you have 1 over 2 pi square root S expectation of minus, say, x minus c squared divided by 2s squared dx. And let's say this is around from some, say, c minus some value, let's call it lambda to c plus lambda. Okay? Yeah. Then this is clearly bounded from above by 2 times lambda. So what I do is the integral c minus lambda c plus lambda 1 over 2 pi square root s times, and now I take this to be 1. This is upper bounded by 1, right? dx. Okay? So this is less than, and now this is a constant independent of x. And this has length. So this is 2 lambda divided by 2 square root pi s. Okay. So you see that if you want that to be a constant independent of s, lambda should be some constant times s. Okay. Otherwise, you won't get anything that's with constant probability. Okay. So you need to get around a little bit around the mean to get anything of constant probability. And that's also true for our other distribution over here, which you can see has the same argument obviously applies to this function here, right? If I take this here, okay, doesn't really matter because the maximum value is still at x is equal to c. Anything is upper bounded by 1 over s. You see that 2 pi, square root 2 pi, that's gone. But anyway, okay. So this is why we have this standard deviation. You want constant probability, go a constant number of standard deviations around the mean before you get anything that's constant. Another thing is that I want to explain, because later on we'll see some funny looking functions or some funny looking expressions. So now assume that I have some security parameter n, okay? And I want this function here, or this probability, to be negligible in n. Okay? Maybe I shouldn't use n, maybe I should use, can I use lambda? Yeah, so lambda is my security parameter. And I want this probability x minus c larger rs should be negligible. Okay? Okay, so obviously, upper bounded. Obviously, if this here becomes negligible in n, in lambda, then I'm done. Huh? Okay? So suffices to make e to the minus r divided by 2, doesn't really matter, negligible. Yeah? Okay? So what does that mean? So e to the minus r squared divided by 2 should be something like lambda minus, and now I get an expression that's called omega of 1. Okay? Omega of 1 means it's a function that goes to infinity as n goes to infinity, or lambda goes to infinity. So this here simply means omega, the limit of lambda to infinity of omega of lambda is infinity. Okay? Then this is going to be negligible. That's exactly what we mean by negligible. It goes faster to 0 than any inverse polynomial. So we have some, so you can write this as some function lambda to the minus g times lambda. And we must have that lambda is unbounded. Yeah? Because if it's bounded by a constant, then this is not negligible. Yeah? And that's why we use this here. And now we can easily work with this and get some funny looking function. So if you do that, this is equivalent to saying that r squared divided by 2 is some, and now I can say, take this here as log, or ln lambda, ln, the natural logarithm of lambda times omega of 1. Okay? Which I can also write as some function that grows strictly faster than than the natural logarithm of lambda. Because I multiply this by some function that goes to infinity. So this is a function that goes faster to infinity than ln of lambda. But that means, so let's just ignore this part here. This means that r must be of the form square root of omega, and then because I can also take the natural logarithm, okay? The logarithm to base 2. Okay? So if I take r to be of this form, then I get something that for which this probability becomes negligible. So it's of this form, the square root of a function that goes to infinity faster than log of lambda. And that's, it's just here comes the log, here comes the square root, that's it. Okay? Looks mysterious at first, but it's not very difficult actually. We'll see this function later, and then you should remember that it has something to do with this here. Okay. Now, we are usually not interested in one-dimensional Gaussian distributions. We are interested in multivariate Gaussian distributions. Okay? We are not interested in one-dimensional lattices. One-dimensional lattices are pretty boring. We know them. You should think about what a one-dimensional lattice is. You can classify them completely. And in for the n-dimensional, the density function for the n-dimensional Gaussian or normal distribution with a mean is now an n-dimensional vector, a vector in R to the n, and the standard deviation is still a positive real number. And the thing is that it's still this factor in front of it, 1 over 2 pi s squared times raised to the power n divided by 2. Yeah, so you get, or you could also say this is square root of 2 pi times s and then raise it to the power of n. And then you see that it's a generalization of the previous one. And then you have the expectation of minus. Now you take the squared Euclidean distance between x and c and divide it by 2s squared. Okay. And you can again look at the expectation of this thing. This should be a bold-faced x. And it turns out that it's c. And you can look at the appropriately defined standard deviation, and this is s. Okay. Okay. They look like this. They are symmetric. And symmetric in the sense that they are rotation invariant. Right? This here, this is a density function. This thing here, maybe go. This thing here only depends on the distance of x to c. Okay? So on all elements that have the same distance, so all spheres around c, the density function is constant. Yeah? So in the plane, if you have here your c, then on all circles around this thing, the density function is constant, because on this, by definition, on all these things they have the density function is the same, depending only on the distance. Okay. And again, we use a slightly different notation just to annoy you. In crypto, again, we do rho sc of x. We plug in a pi in front. We drop the 2, and that gives us this. And then it turns out this is not a density function because its integral, its n-dimensional integral, is not 1. Turns out it's s to the n. simple substitution, application of substitution rule here. It's s to the n, so you normalize by 1 over s to the n, and then you have a true density function with roughly the same properties. Okay? So everything's a little bit scaled by. It's 2 pi. No? If you see, look at this here, from here to here, the difference is 2 pi, right? Because you have to kill the 2 here, and then you have to get the pi here. And that explains why you have this 2 pi not in front. So, okay. And also, yeah. If you look at this guy here, let's go back here. You know, always remember it easily. Here we have a square. That's why the s is here linearly. And we have the 2 here, which is the square root of 2 squared. Hence, we have a square root of 2 here. And you have the pi in there. But I can never remember it. Okay, so this is how we use this in crypto. Again, as we'll see later, we often use quotient of these things. Then this 1 over s to the n disappears anyway. Doesn't really matter. So here's the picture of it. And then again, we can take a random variable with density function 2sc. And again, now here I don't just look at intervals or cubes. You can actually look at all, have to be very careful, measurable sets. And then ending up in this set is simply you take the integral over this set of this density function. But this integral must exist, otherwise. And integrals do not always exist. And if you look at the box, axis parallel box, B, you get something like this. Actually, this is not true. I should have said this is obviously centered around C. Right? A box centered around C. Well, even that is true. Yeah, even that is true. Yeah. Yeah. So you take the n-fold integral. But anyway. And what we have here again is there is a constant a such that for all s, at least, and we have that if the probability, if we choose an x according to this distribution, that its distance to c is at least lambda times the standard deviation is again bounded by roughly e to the minus lambda square. There's a constant in front of it. So we'll think of it this here. Okay. The easiest case is if you take lambda to be square root of n. If you take lambda to be square root of n, then this roughly becomes e to the minus n, or e to the minus n. But again, if you want to make that negligible, you would take this. If you want to make that negligible in the dimension n, well, then lambda is n. And again, you can also show that if you want to have some constant probability, you need to go at least a few standard deviations around the mean. Otherwise, you won't get it. And again, you see that here, you need at least something that kills this term, right? And that means, well, to the n, if you take boxes or a cube, all side lengths the same, then the volume of that cube is side lengths to the n, or 2 times side lengths to the n. And that has to kill this here. And hence the side length should be at least S, something like S. It's the same argument as we used here. You always have to go. So the interesting thing is that this is not too bad, although it looks like going from here to here is pretty bad. But in a small range, it's not that bad. Okay. Okay. Because you can see if I take this here to be, again, S, x minus c, roughly x, then this here becomes e to some constant. Okay, and then it's not so bad. Okay? You see that? So if I make this here some constant times s, this part here, then this is independent of s. Yeah, good. I'm done. I can see that there is some. So that's not too difficult to see. That you need at least that much. Okay, so this is this, this is this, this is this. And often, in particular later on, I will replace this by simply saying DSC. I viewed DSC, this distribution, as a random variable, sort of. That produces elements in R to the n. Okay? So this pick something according to this distribution. And then this also includes that I take the minus, the distance to C itself. You will often see that. It's just getting used to. Good. Huh? So, but in crypto, we are not interested in, mostly not interested in Gaussians on R to the n. We are interested in Gaussians that are only defined, that are density function on elements in some lattice L. Okay? So that have a non-constant, non-zero, and in this time it's really probability on lattice elements. And to define that, let L be an n-dimensional lattice, let C be a point in R to the n, and S, again, R plus. Then we define the distribution DLSC on lambda. And now it's really a distribution. It's no longer a density function, it's a distribution, because a lattice is discrete. And now every lattice point gets a probability. And the only difference to finite discrete probability spaces is now that we don't look necessarily at finite sums, but at infinite series when we sum up things. Yeah? So so we have finite sums, we have infinite series, and then we have integrals. Yeah? So this is something in between. And the way we define it is we take rho s, the probability of this distribution at point x is rho s c of x, and I divide this all by rho s of L, where this term is simply defined to be rho s, c of L. I sum up over all z in the lattice this probability. Or this function, it's not a probability. Okay? And what one has to show is that this term is finite. Right? Because if it's infinite, then all these things would be zero and no probability distributions. If this is finite, then this is a probability distribution, because if I sum up over all elements in the lattice, as usual, if I sum up all probabilities in the probability space, or integrate, then there should give us 1. Okay? If this is finite, then I can do that, and obviously then I get 1, because that's exactly the normalization factor that I put in the numerator and the denominator. Yeah? So, and what one can show, and I won't do it, this term here is, for every lattice, this is a finite value, a positive finite value. Actually, it's not too difficult to do that. But never mind. It's like step functions, and then you take, look, you replace a Gaussian distribution on each parallel pipette, you replace it by one of the parallel pipette of letters. You take this point, and then you replace it by the leftmost corner in that which is the lattice point. Yep. Then you can argue that on this parallel pipette, the difference in the probabilities is bounded by some constant, and then you can easily show that this is actually a constant, not too difficult. So the remarks are, since we normalize this DLS, C, this is actually a distribution. And because of the normalization, it does not matter whether we, in this definition, we take this rho SC or the DSC, because they differ just by a normalization factor of themselves. And that normalization factor, since we take the quotient here, disappears anyway. So that's what we have here. So these are, and here's one of the nice pictures of Oded Regev. So here's a two-dimensional lattice. These are these stars. And you can see the probability at each point. So it's really, it looks like, you take this bell-shaped curve and you only look at it at these certain lattice points. You discretize it. Okay? But it has still this nice bell-shaped, still this nice bell shape. Okay? And again, if two lattice points have the same distance to the C, then they will have the same probability. So again, they have these things are rotation invariant. So they look very nice. Okay. Good. And again, you can, if you look at it, where is this probability distribution maximized? Or yeah, where is the maximal distribution? C is not necessarily a lattice point. Yeah, it's the point that are closest to C are the ones that have are most likely ones. And if you take C to be 0, and you have, again, the most likely lattice point is the 0 then. But then the shortest ones are the next most likely elements. So that's why you can imagine that this is really a good, nice distribution, because if you analyze this thing, you can make hope that you can actually find good lattice points. Okay? Okay, and today I will mostly talk about the cryptographic uses of this Gaussian, but there is also theoretically the fastest algorithms to compute shortest vectors exactly use Gaussian distributions. They use exactly, well, in a very clever way and highly non-trivial, they use these observations. But it's highly non-trivial. Okay. Good. So this is how these things look. Good. Yep. And we can actually generalize Gaussian distributions on lattices easily or directly to Gaussian distribution on cosets of lattices. So coset of a lattice is you fix some v in r to the n, and then you look at all points of the form v plus L. Okay? That's a coset of a lattice. And we can define the lattice distribution D, V plus L, S, C. We do it exactly the same way. For every x that is in that set, we take this row S, C, x, and then we normalize. And again, one can show that, well, this normalization is as before, and this again is finite, no matter what V and L are. Okay? Okay. And let me just, argue, it's just you have to look at it. But it's something that we'll use kind of later, maybe not even later, but soon. So if I have this term rho S, C of x plus v, which is the exponential of minus x plus v minus c squared divided by, oops, here's a pi missing, by s squared. Okay? Yeah, I just rewrite it. This is the exponential of minus pi x minus c minus v squared divided by s squared. Okay? But this is nothing but rho s, the same, but now I shift it to center. It's like I shift the center minus v, and now I take just x. Okay? Okay? So you can sort of push that here into the index here, but you have to make this sign change. That's because of the minus in there. And then you can easily see that this is also true. Okay? Since this is true for every x, then I can also, if I sum up over all these things, I can also sum up over the lattice and use this function here. It's different when I look at this here. That's a different story. We'll look at it later. Yeah? But since it's true for everything, we can just write it also in this way. So at least, and then you can see, well, if we already know that this is always finite for any s and c minus v, then, well, these are all finite. So that's straightforward. We'll use that later. Okay. Some simplifying conventions. If c is the origin, I just drop it. If s is 1, I drop it. If I don't write anything, that means s is 1, c is 0. So it's a density, well, it's a density function, and it's not really a density function. It's a function with a mean and the standard deviation. It's not really a density function. Well, no, it's true. It's a density function, sorry, because I have to normalize by 1 over s. S is 1, so it's a density function, sorry. The inverse of 1 is still 1. Okay? Okay. Okay, let me explain this shift a little bit more. And here I use some funny notation. Okay, so let's look at really, and I just do this. Yeah. Let's assume that the C is 0. To make life a little bit easier. And now I want to look at dv plus ls, and since I dropped the 0, whenever I drop, there's no C in the index set, it's 0. If there is no S, it's 1. Okay? So, and then for every x in v plus lambda plus L, we can write it as x is v plus some lattice vector. Okay? That's why it's in there. For z and L. And then we can write that this probability here of x, this should be a boldface, x is rho s of x divided by this here. Yeah? Plugging in this term here, I get that rho s of v plus z and rho s v plus L. Okay? Now I use this equality with C being 0. So this part here is rho s minus v of z, and here rho s minus v of L. Okay? Okay, so which means that in this distribution and in this distribution, x, the probability of x in this distribution is the same as the probability of minus of z in this distribution here, where x and z are related by this fact here. Okay. Instead of looking at the probability of x here, I can look at the probability of z in here. Okay. Which means if I want to generate an element according to this distribution, what I can do is I generate an element according to this distribution and add v. Okay? That gives me every element with the same distribution as before. Because this z has in this distribution the same probability as this x in here. So I generate z with the right probability distribution, and then I write it as this x plus z. Yeah? No, it's v. V is fixed. The v is fixed. It's a shift. So I look at the shifted lattice, and instead of generating something directly from the shifted lattice, I generate something from the lattice and then I shift. And the way what I said here is that instead of the probability of picking according to the shifted lattice from this, we can also pick according from the lattice and then shift according to this distribution. Okay. Okay. This is the meaning of these things where we really look. This is then, pick something according to this distribution, an element according to this distribution. So we can describe Gaussians on cosets of lattices as shifts of Gaussians on lattices. This should be on. This is a nice and useful observation. Okay, good. Yeah, so And that's so in particular, what this means, if I pick something according to this thing that is short, then this something plus v will be short, because its difference to this guy is minus is short. So x plus v is short. That's the meaning of it. It's, for me, it takes, every time I look at it, it takes some time to digest it, but that's what it does. Picking here something that's short, its difference to minus v is short, so if I add it to this, this is short. Not the vector itself is short, but this thing is short. Okay, now comes the interesting part. A Gaussian distribution on a lattice looks like this. But it turns out that it doesn't always behave exactly like a Gaussian, like you would expect it to behave, as if it's continuous. You would always say, well, like discrete, but well, let's pretend it's continuous, and then things will carry over. Turns out that that's not really true because of the discrete structure. You can easily imagine that if I take a very, very small deviation, then everything's concentrated on the mean, on 0. And then the discrete structure, well, yeah, even in the continuous one, there's still stuff around it. But in the discrete case, there is nothing around it. Right? The next lattice point, if I take C to be 0, the origin, is far away compared to S. So there is nothing around it that I can say, well, there's something around so that it's not always concentrated on these. No, it's not true. So there must be, you should expect that, well, yeah, I need to have an S that sort of, if I look at everything of distance S around it, I capture other lattice points. I capture sufficiently many other lattice points, sort of, so that it's not all concentrated on this point in the middle. Okay? This leads to the smoothing parameter, which I'm not going to define exactly, mathematically. This involves the so-called dual of a lattice, and never mind. I hope that it's just a parameter that says if some S is larger than the smoothing parameter, then things behave nicely. And you don't need to know how exactly it's defined. We need to know bounds on it, lower bounds on it, but that's it. Okay? And some of the interesting properties are true already if S is at least the smoothing parameter, or it's some constant larger than the smoothing parameter, or some function of this thing larger. Okay? And the smoothing parameter also gets a parameter epsilon. And epsilon measures how far away it's from what we should expect. Okay? And so, for example, if S is larger than this eta epsilon of L, then this distribution, DLC, is concentrated like a Gaussian distribution with deviation S up to an error term that can be expressed only with epsilon. Yeah? Roughly. Another property is there is an efficient algorithm that approximately samples lattice points according to this thing. S needs to be much larger, and related distributions. and this approximately, how well does it approximate this distribution depends on epsilon. Okay? So what's the statistical difference between the two distributions? Can be measured in epsilon. And also the overall density of L is almost shift independent, which means that whether I look at this distribution, or well, I can go further back, I think. No, where is it? Yeah, whether I look at this thing here or without this doesn't really matter. It's almost the same. So if you, and that's the interesting thing. So if you shift the lattice a little bit, this term here doesn't change a lot, which means that it's sort of this, the discrete structure is gone. Right? Because if you again look at something that's is that true? Should I do that? Should I say that? Yep. So if you take the origin and look at this row S of L with 0, and now you have some C that's sort of as far away as everything you can imagine from a lattice point. Okay? Yeah. So this thing has its peak at C and things that are C plus some lattice point, but never at a lattice point. Right? And now you take this thing here, overall, and that's almost 0. Because there is nothing close in the lattice to it, if you think of it in terms of this here. There is nothing. Okay? And hence, these things do behave differently. So it blurs out basically the discrete structure of it. And there are many other things that you can have. And I will mention just a few. Okay. So Gauss smoothing parameter is something that, if it's large enough, then things behave nicely. And here is and I won't, probably then I will stop for today, because then otherwise I'll go through all these. Or does that make sense? I will talk a little bit about this here, because this is, okay. So here's a theorem that goes back to Picard, Vaikuntalantan, and Gentry, I think, yes. So let L in R to the n be a lattice, and we are given any basis. And let epsilon be 0. And we denote by B tilde the Gram-Schmidt orthogonalization. I'll explain this on the next slide. Some version of B, which is not a lattice basis, but it's a basis of R to the n. Then we have that eta epsilon of L is bounded by the length of this B tilde, so the length of the longest vector in it, times this expression here, divided by pi, never mind. Pi often creeps up in these things. And then you have ln 2n times 1 plus 1 over epsilon. Okay. Yeah. So this, if you're farther away than this, then this behaves really nicely. Okay. Don't read this sentence down here for the time being. Okay. So let's look at something. For example, we want epsilon to be really, really small. Okay. Say epsilon should be e to the minus n, or 2 to the minus n, something. So we want it, let's do 2 to the minus n. Okay. Okay, then we have this ln. Let's look at this without the square root. But you should remember, you should recognize something here, right? There's a square root, there's a log involved. Yeah. Deeply inside the proof, there's hidden this stuff over there. Okay. So then we have, what we have there is L2n times 1 over 2 to the, and then here 2 to the n, right? Okay. Which is roughly ln of n times 2 to the n plus 1. Okay? Which is roughly ln of 2. It's actually the same even. Never mind, plus ln n, right? Okay? Which is roughly, never mind the logs and ln, this is roughly n plus 1 plus ln n. Okay, which is roughly n. Okay? So if I'm n times larger than, if I take something like b tilde length times n, then I'm good. Okay? Then the smoothing parameter is at most like, so what I will do, I will always take this as my value for the smoothing parameter. Pretend that this is the smoothing parameter. And then it's even better. Okay? No? Okay? No? So we will always replace, well, we achieve some eta. We say, okay, let's, instead of working with this parameter, we'd work with this parameter because it's even better. Making the parameter larger makes it better. Smoothing it out even further makes it better. Why is it called smoothing it out? If you make s larger, then the probabilities get more even, right? Because everything is divided in the exponent by s squared. So this distance doesn't matter as much as for small s. You see that. If I make this large, if it goes to infinity, this becomes 0. And then everything's, well, almost the same probability. Doesn't matter. Obviously not true because you cannot do it infinitely, but it's far out there. Okay, but what we are often interested in is epsilons that are negligible in n. Okay? And again, similar argument like this, if I take this epsilon to be of this form here, n to the minus omega of 1. This is my epsilon. Epsilon is epsilon of n. Okay? Then I'm negligible. So if I plug in such a thing in here, forget about this plus 1 here. It's only there for technical reasons. And to make this statement true also for epsilon larger than 1. Never mind. Okay? Then I have that n times n to the minus omega of n is still some n to the minus omega of n. This omega of n goes faster to infinity than any constant. So if I add or subtract a minus 1, doesn't matter. Okay? And then I have that this here becomes ln of n to the minus omega of n. Right? So this is what we get in here. Forget about the pi, I don't care. It's a constant. But this, as we have seen, omega of 1, sorry, I should have. But this here is 2 to the minus omega of ln n, as before. Little omega. Push this into the exponent. Then, or e, let's do this e. And let's say here's a 2 in front. Then this here, and now I take the ln of it. So this becomes omega of ln n. And then I take the square root. And the square root I can push inside the omega. Which means for any function, and now I'd use some particular function that goes to infinity at least as faster than square root of log n, or ln n, there is a negligible epsilon n, which I just depicted here basically, n to the minus g, or 2 to the minus epsilon of n, such that this smoothing parameter is bounded by this b tilde length times omega of log n. And this is a term that's often used to optimize parameters. But you can see that, well, it's not something that you would not expect to creep up if you talk about Gaussians. It comes naturally in Gaussians because we have this exponential of a square. And this omega, just we want to have something that's negligible. Okay? So in practice, what we'll do is we have some epsilon that we want to achieve, and then say, okay, let's say that we know that the smoothing parameter is bounded by this here, upper bounded. So if we work with this here as our estimate for the smoothing parameter, we are better. We can only do better, not worse. So our approximations to distributions, our deviations from certain distributions is not worse than something that is determined by this epsilon. Okay. And this is the next to last thing. There are several other upper bounds on omega, on eta epsilon of L, relating it to lambda 1 of L, so the shortest vector, length of the shortest vector, lambda n of the thing, of the dual, and all kinds of things. But I think this is, by now, this is the most common one and the most useful one. And here's the definition of the Gram-Schmidt orthogonalization. This is really just briefly what I say. So if we are given any set K of linearly independent vectors in R to the n, then we define the Gram-Schmidt version or Gram-Schmidt orthogonalization of it by setting b tilde 1 is b1. And for I from 2 to k, we subtract from bi the inner product of bi comma bj tilde divided by bj tilde inner product with itself, and times bj tilde, do the sum of it. Why are we doing that? These things are pairwise orthogonal. Easy to see. Take the inner product of this guy with bj tilde. Let me just do that here. So b I tilde comma bj tilde, and j is less than I without loss of generality. Otherwise, you reverse the order, and then it's just take the complement, never mind. This is bi comma bj tilde minus sum j from 1 to I minus 1, bi comma bj tilde, always the inner product, the usual inner product in R to the n, times, and now I take the inner product. The inner product is bilinear, bj tilde comma bj tilde. Okay, and now I did something wrong. This should be, let me say this is k is less than I, and I do a k here, and I do a k here, and then I should do a k, no k here, but here I should do a k. Yeah. And now by induction, you can argue, well, if I know already that certain things are linearly independent. This is true for I minus 1. Then these become all 0 except for k is equal to j. This cancels here. There's just one term in here, and that gets here. Period. Yeah. Has nice, so it's pairwise orthogonal. The span is the same, so I didn't require that k is equal to n, or that they are the basis for r to the n, but the span, the linear span, the r linear span is the same. However, if B is the basis of some lattice, then this is no longer in general lattice basis, simply because these vectors are in general not in L, because we have here rational coefficients and not integer coefficients. Okay, so that's no longer true. Here's a picture in 2D. We have B1, B2. B1 is the same. And then what you do is you project down here. You look at the projection down here and subtract this thing. So it's like the orthogonal complement here in that from here to here. So this guy can be written as some part in this B1 tilde, and then you take something in the orthogonal complement, and that's it. And in R3, you can do that and look at two-dimensional, what sticks out, and then three-dimensional up to 4, and so on. Okay, and that's it, I guess, for today. Next time I'll talk about a little bit about the important properties that we have, and then that fits nicely. Then we'll see how we can use, given these things and using some of these properties, we can construct a pre-image sampleable function family given lattices. Once we have that, we can define signature schemes. And then I'll also talk about the LW and LW-based encryption scheme. Okay, and that's it for today, unless there are questions. No? No, good.